So what is unstructured data? So before I talk about unstructured data, I just wanted to give you a perspective of the different type of workloads and use cases that we see in storage. This is not an exhaustive list. We just showed you some, give you a perspective. There are different type of storage workloads and use cases. So there are these IT workloads and use cases. Some of them you may be familiar with, whether it's virtual servers, databases, file shares, video surveillance, and then what we call our production workloads. So think of these as the workloads that a company would be using it, that would be part of their core competency. So think of, say, for example, media and entertainment company, right? So making a movie, doing rendering, that's part of their core competency. They make movies, right? So that's basically, think of it as rendering would be a core production workload. Now that movie company may have their own email servers and databases and stuff like that. That would be the IT department of that company out here. Right? So you have the production workloads, and you can see a whole bunch of verticals out there. You have the IT workloads, which just sort of spans across across these verticals. And then we have some emerging workloads, such as think of things like automated driving assist nowadays, AI, ML, and so on. Right? So basically, broadly classifying it into these three buckets. So when I talk of unstructured, it basically spans all of these production workloads, most of these production workloads, lot of the emerging workloads, and then some of these IT workloads, right? So think of basically anything which is dealing with files, things which is basically dealing with objects. That's basically what we call unstructured data. Right? So, and that's basically where Isilon and our unstructured data portfolio plays. Just a quick stat out here. So if you look at all the data in the world today, 80% of that data is unstructured. So that's basically where we play. It's a growing market. If you see most of this data, if you see where the growth is happening, most of that growth is happening in the unstructured space, right? So whether say if you look at, like, for example, automated driving, all these cars driving, collecting images, right? That data is growing much faster than, say, for example, your databases or anything else like that, right? So it's growing, and it's also the largest part of the data world, as I said, is unstructured. So if you look at our unstructured data portfolio, basically we have two big products out there. We have Isilon, that's our scale-out NAS product, and then we have ECS, which is our scale-out object product. Here are some stats out here. I mean, for Isilon, we have today about 17,000 plus customers. ECS, which was launched much later, we have about 3,000 plus customers, and you can see some of the capacities that we have shipped across both of these platforms. On this side of the slide, we are also showing you the latest Gartner Magic Quadrant for distributed file systems. That's what they call unstructured distributed file systems and object. And as you can see, Dell EMC is in the leaders quadrant right at the top. And this has been there for almost 4 years now, consecutive years running now. So we are way ahead of where the rest of the field is. So the question is, why is this so, right? What makes us so unique that makes us be there in that leaders quadrant for 4 years in a row? So, and for that, we're going to talk about what makes Isilon unique, what makes us so different, and so on. And that's basically the rest of the presentation is all about. Before we do that, just wanted to show you something. So so Isilon has been playing in this vertical, in the media and entertainment vertical, for many years. Many of the movies and productions that you have seen were actually based on Isilon when it comes to rendering and so on, right? So the entertainment industry decided to acknowledge that and presented us with this Emmy, for which we are extremely thankful. So with that, I'm going to hand it over to Callan, who's going to walk you through what makes Isilon now make it so unique, what makes us be the #1 player for 4 years in a row now. Callan.
Thanks, Kaushik. All right. Yeah, so specifically that award was around our tiering functionality, which we will cover a little bit today. So what I'm going to do is I'm going to go through the basics. So Kaushik's actually helped build a nice, simple deck, and we're going to keep it all very simple because some of you probably have never actually seen or heard of OneFS or worked with it. So the first thing is that you sometimes hear OneFS and Isilon used interchangeably, and that's where some people sometimes get a little bit confused. So OneFS is the core operating system that Isilon as a product runs on, right? So OneFS is both the file system itself. It does all the volume management, which we'll get into. We don't actually do any of that stuff. And so all the traditional things you would think of to do with that, we do. All the data services, all of the bits of components come in and form what we call Isilon, or what we call OneFS. So what we do is we take this and we wrap this up into an offering, and that offering we call Isilon as a product. OneFS today we can put onto some virtual hardware, we can put it onto appliances that we have predefined. We'll talk a little bit later on about some of the cloud offerings we're doing as well. So you often hear the term, scale out, and you hear the term NAS. So Isilon is a scale-out NAS, scale network attached storage system. It supports many different protocols that many of the industry players use today. And what that allows us to do is create a very flexible, extensible system, right? So Isilons are used as the sort of like the holding place for a lot of data for different organizations around the world. Some of the customers I've gotten to meet in my time in Asia Pac, it's been interesting seeing the weird and wonderful ways Isilons are used to store data. So how it all comes together is we have this term of what we call scale out, or node-based scale out. So what we do is we take an individual node, and what a node is for us is it's a piece of commodity hardware, or it's an instance if we're talking about some of the offerings we have in the future. And what this node is it's effectively a ratio of performance and capacity. And there's different types of nodes. So you can imagine some customers need very performance-dense nodes. Other customers need just purely capacity. So our teams and our partners help customers understand what type of node configuration they need. They take a node and it becomes like a building block, right? You take multiple blocks and you want to build these little castles. So depending on the architecture that we use in our current generation of hardware appliances, you need to start with at least 4 nodes. In others, it's 3. And these 4 nodes talk to each other over a dedicated redundant backplane. And this redundant backplane is what allows each of these nodes to talk to each other. So they can do things like they can share memory. They all have effectively a coherent view of the file system. So there's one single file system that is stretched across all the nodes in the cluster, and we can control it from an individual node. So what I haven't shown here, because this is meant to be the 1,000-foot view, and then we'll go into a little bit more detail, is that we obviously connect each of these nodes into the customer's network. And a customer's workflow can touch any of these nodes, and they can get access to any file on the operating system or on the file system itself. So what we do from here is that when a file comes in, let's say it comes into node 3 and it's written to the cluster, to the file system, we distribute that data across all the nodes in the cluster, or in the node pool to be specific. So let's say you have a large, we talked about the Emmy Award before, so let's say you've got a very large file that you're doing in a media entertainment type use case. we'll take that file, we'll split it up, and we'll distribute it across all the various drives and nodes that we have in the particular pool. What we can then do is we can actually extend dynamically. So we can add nodes as we go, and a process will kick off, and it'll actually take those files and it'll move them across and automatically distribute them across the various nodes in the cluster. So when we say scale out, what we mean by that is it's policy-based management. So just because we have a thing called a node and you can add multiple nodes, that doesn't necessarily mean that it's scale out, right? What makes it scale out is it needs to be elastic. You need to be able to expand it easier. We need to be able to take one of these nodes away, for example, which is what allows us to do some very creative options with tech refresh. We have also other options around how we commercially sell these nodes, so each node can have its own maintenance window. So there's lots of advantages to doing this, and we'll cover that in a bit more detail. But the other thing we can do, and this is sort of linked to the actual Emmy Award, is we can introduce different types of nodes, right? So in this example, I've just drawn another 4 green nodes, and let's say the customer started off and they came to our pre-sales team and they say, look, I've got a media entertainment workload and I need this much performance, or they think they need this much performance. So traditionally, they might have gone to another architecture that we have, or a different vendor or whatever, and they would have had to estimate how much performance they needed up front, and they'd build a controller to suit that. But it's very difficult to do that, right? Things change, people find it really difficult to pick where they need to be. So what would happen is, in a lot of cases, is they might start with the blue nodes, let's say they're performance nodes, and they realize that at node 6, they're meeting their performance goals. They don't need any more performance. So what they can do is they can add the green nodes in, or the capacity dense nodes, and they can get more capacity for each one of those nodes, keeping in mind that the OneFS file system is stretched across all the nodes. The same, we can extend the different pools, and while I've made these even, they don't have to be even. In fact, they're never even. It's usually always a little bit of performance and a lot of archive, but it depends on the workload. What we can do, though, is we can do a lot of different things. But the specific thing I wanted to talk about was our tiering technology. So we can divide these into logical groups, keeping in mind the file system's still spread across the whole lot, but then we can make rules, right? And the rule might say, hey, for this type of workload, it's a backup archive workload. I don't need it to have performance. So I can send it directly to the green and not even worry about it. Or I could send the work to the blue nodes, let it sit there for a period of time, and then the system will automatically move it off onto the green, all right? The other thing with OneFS that comes in the file system and the data services and all of it being together is that we don't actually, there's no traditional constructs such as RAID groups or LUNs or anything like that. So we don't need to worry about managing any one of these individual nodes. And that's why when we say true scale out, that's effectively what we mean, is that each one of these nodes is independent. It can access the file system coherently, so users can get access to the data no matter which one they ask for, or which node they talk to. And if we need to, we can even remove nodes, which we'll talk about.
With the tiering aspect, does the whole file move, or maybe it's just parts of it? I'm thinking, like VMDKs and the like.
Yeah. So from a tiering perspective, within the cluster, generally the entire file, the intent is the entire file will move. There are cases where it may not, but generally the whole file will move between the individual tiers, and that's all completely transparent to the user. So when it comes to tiering within the cluster, there's no stubbing or anything like that. It's all done below the file system, so the user has no idea where the data is. Yeah.
But I just wanted to also add the fact that while the file is not getting split, we do have the ability to keep the file in one tier and its snapshots in a different tier.
Okay, that's nice.
Right? So,
yeah, so we can get quite creative with our stuff there. So is there any questions there? Otherwise, I'll move on to a bit more detail. Okay. So what about our architecture? Obviously, you've seen the market quadrant, and it shows that we're leaders. The top 3 we have a separate slide on, so I'm not going to cover those just now. But simplicity is scale, right? So I've already talked about the fact that in order for something for one person to manage, 50 petabytes, and because teams aren't getting bigger, so the amount of storage people need to manage is increasing, right? So everything needs to be policy-based. So, our snapshotting, all our data services, our tiering, all of that is just a policy that you write, and then you let the system do the hard work. That's what we mean by easy to manage. And there's various articles and documents out there on that. Multi-protocol. So today, workloads are getting more and more complicated, and there's a lot of collaboration that's needed. So we can allow workloads to natively write in over one protocol and then be read off another protocol. So you can have, for example, like collection systems that write a certain type of collection protocol. Let's say it's NFS. And then you've got users that need to look at that over a Windows-based system and they want to use SMB. So we can do those collaboration style workloads. We can do all that as well. And then there's a flexible architecture. So there's many ways that we offer Isilon, as I said at the start, right? So that is down to purpose-built appliances for performance. And we'll talk a little bit later on about some of the public cloud stuff that we're doing. So when it comes to unbounded scaling, we have this concept called auto balance. And what that basically means is we can have the 3 nodes that are shown here. We have the back-end network, everything's interconnected, and all the nodes can talk to each other. So they've got a constant view of what's happening in the system, in the distributed file system that we have. We can then add nodes as we go, and what will happen is that file system will automatically expand across the additional nodes. There's nothing to do. You don't even have to tell it to do that. It just does it. So what that gives us is it gives us a way to linearly scale performance and capacity, and they're both just as important as each other, right? Just because you can grow something really big, if it doesn't perform, it wouldn't make sense to our workloads, especially some of the technical computing workloads that we do a lot of work in lately, like machine learning or deep learning, or even the media entertainment stuff, right? People want it to be easy. So non-disruptive scaling means that we don't actually have to take an outage. There's nothing to happen. Once we add the nodes, it just automatically does it. And again, the automated rebalancing, we take the file and we actually restripe them automatically. So the one other thing that I want to point out there is, let's say we started with 3 nodes, just to make this really simple. It's not. This is taking a little bit of liberties, but let's assume that 1 node is used for protection. So that means our files have 2 usable for 1 non-usable. So they're 2/3 efficient, effectively. As we expand the cluster, that increases in efficiency. So those big files that someone like one of the media houses, because I don't know if I'm actually allowed to say which ones, as they use storing really large files, they add additional nodes that they need for more capacity and more performance, and at the same time, they get more storage efficiency at the same time, right? And again, just stop me at any point if you have any questions. We've always got the whiteboard if we want to go into more detail. So one file system, so basically what this shows is as a file's written into one of the nodes, that node distributes the file across the whole cluster, and that file can then be accessed by any of the nodes. So again, you can then do some very creative things with how the users access the system, or you can just let all the users access to everything. When we expand the file system by adding nodes, we also expand the way the users talk to the file system, which means that you don't even have to reconfigure that. They'll just get more performance grunt over time.
Callan, so question for you on that. When you've got many parallel users all logging in and accessing the system at the same time, how are you distributing which node they connect to?
Yep.
And making sure that you're not bottlenecking of individual nodes with connections.
Yep. So basically, there's a feature called Smart Connect, and what that Smart Connect process does is it's like a intelligent load balancer that fits into the customer's environment. So it actually plugs into the DNS infrastructure. It's not in-band, which means you don't talk to Smart Connect. Smart Connect is in the data path. It just points the client to where it needs to go. Smart Connect understands how busy all the nodes are and understands how busy the drives are, and it does the dynamic distribution. And it's policy-based as well, so you can have a certain configuration for certain customers. So someone like media entertainment, for example, they just want to spread everything out as wide as possible in like a render scenario. But if you're talking about a customer that has very large, heavy-hitting servers, and they've only got a small amount of them, they'll be a bit smarter in how they distribute it.
But if you're using a single IP, then you're relying on...
No, so let me clarify that. So each
IP.
individual node has its own IP addressing. So you can talk to each individual node totally separately, and then the Smart Connect process is what controls nodes to it. So basically how it works is there's a name that you do a DNS delegation. That DNS delegation gets delegated to a special DNS server that sits on the Isilon.
Okay.
That's called Smart Connect. And all the IP and stuff behind that is what does the distributions.
Okay, so you do it that one. Okay.
Yeah, and if you want to know more, I'm happy to whiteboard it, or I can do it later after the break, whatever you want to do. You know?
And in terms of the distribution of the data, obviously you're saying you're splitting it up and spreading it and protecting it across multiple nodes. What overhead then is there on keeping that metadata consistent? Because obviously if clients are coming in through different routes and you're accessing different nodes, and they may be, for example, the first node there, that client may connect and permanently be connected through that node for all of its activity. Somebody else comes in and dumps a load of file data through another node. You've now got quite a significant metadata overhead to manage.
Yep, so the metadata overhead, there's two sides to that. So one side of that is that we have clusters today with tens of billions of files. There's no issues with in terms of the amount of metadata. Your question's more around how does one node know where to get the metadata from?
Well, and also there's a locking challenge there that if somebody's doing a lot of reads in one location and somebody's doing a lot of writes in another, you used the example yourself about people putting in NFS data and then reading it through Windows. Potentially you've got locking challenges to make sure that you're managing that heavy write activity on a file system whilst you've got other people who might be putting in and reading it elsewhere.
So Isilon's a totally distributed file system. So if we've got writes coming in on one part of the file system, read coming in from the other, they will obviously not contend with each other at all. The lock contention comes when if there's a workload that needs to hit one particular directory, and then we obviously are POSIX compliant, so we do need to comply with the rules. It does get a little bit more complicated when we're talking about NFS contending with Windows, and I can talk to that, probably not for everyone, but I can go through that for you. Happily go through
probably
that
not,
for you.
but yeah, I understand.
But yeah, so that's how all the data is spread. As far as the question around how does the system know, there's effectively memory structures on each of the nodes, and they know where to point at various bits. So that's how they understand where to find the different things. So when we create a file, we basically create metadata, and that metadata mirrors they obviously don't exist on every single node. So it's got to know where to get them, and that's why that.
So are you distributing the metadata to match the data, or are you distributing the metadata to match the resilience of the cluster?
The resilience of the cluster, which again is policy-based. So you would say in this, the standard configuration is protect against the failure of 2 drives or 1 node. That's the stock standard default. And the write plan, the thing that writes the data down, including data and metadata, it's aware of that. It's aware of all the systems that are in this cluster, what's online, what's not, and it will lay out the data such that it complies to the policy.
Yeah, I just want to add one thing. So you mentioned it earlier, but want to make sure. So this file system is one file system. That's why we call it OneFS, right? It's one file system that spans across all of these nodes. So it's not like a data which comes in here you can come in through any gate, but you access the entire file system, right? So yeah, client comes in here, he has access to all the data. A client comes in through here, he has access to all the data, right? So where the client comes in, his responsibility is to collect all the data, that file that was split, collect it, and send it back to my client, right? So that's the important aspect of it, and that's a very important differentiation that we have versus other file system architectures.
Yeah, and on top of that, just, I know we don't have the time to go into it, but we have a lot of constructs we can create. So if we want to create like an environment that wants to logically separate the Isilon into separate security zones and stuff like that, we can do all that. There's a lot of other things we can do on top of this being just the basic standard story. So I'll continue on then. So then there's the main thing that, like, just because you've got a workload on us, well, you need it for it to be available, right? You need it to be always on. And that's our marketing term for that. And so imagine that there's 2 sides to always on. One is data availability, the other one is data integrity. So from a data availability perspective, if you lose a node or you lose access to a node, we can dynamically move those connections to they can reconnect to another node. And that's because, as Kaushik said, each node has an independent view, has a consistent view of the data. Each one of them can access it. But from a data integrity perspective, let's say this node is actually completely destroyed. Someone burns it or pours water down it or whatever ends up happening, which again, I might add is very rare. what needs to happen is we need to reprotect the data. So one of the other advantages we have here with OneFS over a normal traditional system is we don't have those normal constructs, those layers on layers of RAID architectures and stuff like that. So when we need to rebuild that node or a drive on that node, we can rebuild it to every single other drive and every single other node in the cluster, and we can do it quite fast. And that's what allows us to reprotect data quickly, and that's what allows us to get clusters that are just gigantic, right? Because that's always the biggest thing that people are concerned about, right? Is, okay, it's great that I can put my data on there fast enough and it's available, but how do I ensure that it's going to be there forever, right? And the size that some of these Isilons get to, sometimes people don't back them up because you can't back up 100 petabyte, like, say a 40 petabyte cluster. It just doesn't make sense to do that. They might replicate it or whatever, but it doesn't make sense to.
I have a question.
Yep.
Most of the scale-out file systems are very good at managing large files.
Yep.
But when it comes to smaller and smaller files, they
Yep.
they are very stressed both on the metadata and on the way they store data. So most of the time it's just because they use very large blocks to manage, the
Yep. Yep. So
throughput more than the IOPS. So how do you manage this kind of?
yeah. So basically, what it comes down to is the way even the term small file is changing today, because what used to be a small file 10 years ago versus what is a small file today is very different.
Well, we are talking about the fact that now with the IoT and also in genomics, it's easy to find 4K files.
Yep.
So 4 kilobytes. So we're talking about small files,
Yep.
non-small scale-out file system-like files. So.
Yeah. So I have a slide a little bit later on that talks to that exact point, but just to quickly answer it, we protect files exactly the same, a small file, exactly the same as a large file, with a variable width in which we can stripe it. The disadvantage is when a file is very small, we can't use, even if the cluster is a 100-node cluster, we can only stretch it across a certain number of nodes because it's not big enough. So basically, how we deal with this today is we have technologies to pack those small files. Again, we're talking minuscule files into larger containers, and then we erasure and code the containers just like we're doing here. That's effectively how we do it.
How big is the chunk?
The chunk that we erasure code them into, by default, it's into 1 gig containers we'll put them into, which means they'll store at perfect efficiency. Anything realistically bigger than like let's say a 20 meg file, in most cases, actually even smaller than that, is going to store absolutely perfectly.
So does it mean that when you have to handle very small file, not even talking about 4K, but 32, 64, 108K kind of files, you have a lot of write amplification in the back because you have to consolidate all the files in larger blocks and then read the larger blocks.
Okay, so you're right in the sense that the collection of small files is a post process. So yes, there is it's a background task that happens. But the thing I would say to that is I was a principal solutions engineer for APAC. I saw lots of different customers. Even EDA, so semiconductor customers, they are the customer that has the biggest problem with small files because of the way they do their workload. We have almost complete monopoly on EDA type shops. We do a lot of work with these sorts of guys. So generally, even for them, this amount of small files, like a 4K file is just that. It's still tiny. Even if you have 1 million 4K files, it still doesn't add up to much. So when we look at across the board, generally, a lot of customers, they consider their entire workload they're going to put on it, the small files are a rounding error. But we are looking at other technologies in the future that we can do it even better. But these days, the packing of the files generally meets pretty much most cases of what people need to do. Yeah.
So does that how you deal with data efficiency for usable capacity?
So usable capacity on Isilon is slightly different. We take a raw capacity, and even some of our other architectures, right, that are based on scale-up architectures, they take traditional systems and they carve out LUNs and hot spares, and that presets the right efficiency of that overhead, right? What we do instead is we dynamically do it, which means at write time, when you go to create your file, we dynamically allocate how large we're going to stripe that. Now, the advantage to doing that is that we can store a large 4K movie better than anyone else can. The disadvantage to it is that we don't know our storage efficiency up front because it changes. But what it allows us to do is we can take out a node, we can add a node, and all those data efficiency constructs, all being policy-based, will dynamically change. They'll grow and they'll shrink. So the reason we choose that is we see customers taking advantage of easy manageability. They just want to know that they can put the data there and it just works, right? So just to go finish off the rest of this, so just to show that when a node comes back, the system will automatically detect the node is there and it will reconstruct the data back onto the node as per the policy that's been set. So really, really easy. The main thing that I'll call out on this, just to get back on time, is the non-disruptive tech refresh. So one of the main advantages that customers really love about a technology is if you're going to build a massive enterprise data lake and you're going to have multiple protocols writing into it, all these different collection systems, and you'll say running a deep learning, machine learning algorithm on the back end. So you've got all these interconnected systems, is you do never want to migrate that data. You just want to know that you can land it there and you can life cycle it forever. So what that tech refresh, non-disruptive tech refresh means is because we can life cycle nodes, in other words, we can add nodes and remove nodes non-disruptively, we can recycle an entire cluster. So there's clusters out there today. I have one customer in Australia. They've had Isilon for 11 years, and they have never actually had to migrate their data. They've just cycled through all the various generations of hardware.
So you can actually have like different kind of models within the whole cluster.
Different kind of models, and we support a spread of generations. Obviously, there is a point at which we don't allow you to have like a Gen 3 system. You can't have a Gen 4 system anymore with the latest version of code.
Okay.
But those systems are long since out of maintenance. So.
Yeah, our policy is like an N-2 type of thing. So
Yes.
as long as you do that, but that's a very important aspect, like what you gave that example. So your cluster actually lives on forever, right? That's the beauty of it, right? It's whether software upgrades, hardware upgrades, cluster lives on, right? That's the beauty of it about this technology. Right, and that makes sense, right? So think about it, your multi-petabyte cluster. You don't want to go and replace it, rip it apart, or do anything like that, right? So, so that's the.
How do you manage the different nodes for size of disk? So in many cases you have a ratio between IOPS and terabytes, especially with hard drives.
Yep.
So larger hard drives have less IOPS. So how do you manage the load balancing in a cluster to have a consistent I/O or
So we manage
consistent performance?
We manage it in two ways. So the first way is that we obviously, part of the reason why we got the market leader is the fact of our pre-sales team and our partner team are trained in such a way that we understand how to size environments correctly. Now, as far as how does the technology do that itself, there is multiple levels of load balancing and caching technologies that are within Isilon. Like I could spend an hour just on explaining how all the caching technologies work. Our prefetch technologies and the way we can get a lot of... Okay, so basically the difference between what the client asks for and what the disks actually read or write is caching, right? When it comes to media entertainment workloads in particular, because that's where our heritage is, we developed a lot of proprietary algorithms that allow us to read data off large drives, or large spinning drives, very effectively. And that's to do with how these systems spread the data across all the various nodes and drives in the system and how it works, right? Today, obviously, we have all flash nodes, we have denser nodes, we have all sorts of different things. So what we do is we take every single node and we take it through an engineering process where we do performance validation on it. So we know how much performance a particular node can do. And that's what we use to give these systems understandings of what workload a particular node can take and what nodes we should suggest for a particular customer before they've even purchased
Okay,
it.
so it's a mix of caching and common sense.
Caching, common sense, and then there's a couple of different back-end systems that work, which I can take you through after. Probably best to whiteboard that, but I'm happy to do that as well. Does that answer your question?
Yep.
Cool. I know it's kind of hard because I can't go into enough detail. I'm already getting behind, so I'll just quickly burn through the rest of this. make sure we've got time for questions, and then go from there. So today, this is just quickly what our current Generation 6 hardware looks like. 4RU box, 4 nodes in a box. Each one of these, extremely, extremely dense. So, click that button. Yeah, there's 5 sleds on the front. You pull the sled out. Depending on the type, you've either got 3.5-inch drives or 2.5-inch drives. And they can either be SSDs or spinning drives. All of these systems as well have some back drives as well that are used for metadata caching. So regardless of whatever node you buy today in Gen 6, they all have some degree of SSD that does it at a minimum metadata caching to accelerate that experience for the user. Because that's the main thing.
Is it one drive type per node?
So yes, so it's one drive type per node.
Is it vertically stacked in the front then?
Yeah, so there's 5, and then they look exactly like that. And then yeah, that's right.
Do you also have a software-only version that I can run on standard hardware?
Yeah, so there is a software-only version, and yes, it just comes down to what exactly you want to run that on. Today, we support VMware, but we're looking from a product management perspective as what we do with that in the future. Yep.
Yeah, so the idea, if I buy a Dell server that has enough resources, theoretically, I can run the same software. There is no specific.
I'll let you answer that one because I don't know what I'm
So,
meant to say.
So to your question, do we have a software-defined Isilon today? Yes, we do have a software-defined Isilon today, and that runs on VMware. But there are certain limitations. It's mostly for smaller deployments, right? Not meant for a scale-out large deployment, right? So, but the point that you're bringing up is that, hey, could I build a multi-node cluster with power edge servers and this scale-out file system? That is something not there today, but I'll stop there since this
more for standardizing at the branch office sort of thing.
Yeah, so branch office is different. So you got to remember, most of our customers are looking for capacity and performance at scale for very cheap. Okay. And the way that we do that is we actually have to engineer the appliances generally, because that's the best way that we can get to getting the best dollar per gig for performance, balancing all those things. That's generally why most people buy the appliances. But for edge use cases, that's currently what the virtual solution is mainly targeted for, and we're looking at what we do with that in the future as well.
Yes.
What do you think about the approach your other vendors are choosing, like variable block size?
Variable block size. So do you mean do you mean for
file
DGUP?
Systems, the variable block size for file system.
For the file system block allocation itself?
Yeah, that's their methodology for efficiency.
Yeah, so it comes down to the answer I gave before around like a small file is exactly that. It's a small file. Even 1 billion 1K files isn't actually a lot of space. Today we use a 8K block. So that's even if you create a 1K file, we allocate an 8K block.
Right.
Now, even with that overhead for a 1K file, technically we store 8 times it if you look at it just in that one instance. But even across the board, when we get compared to, in a lot of proof of concepts, we're still found to be more efficient than pretty much every vendor.
And the one thing I just wanted to also add, sorry, I didn't want to interrupt your thing, is the architecture is different, and I want to highlight that aspect of it. It is not like we were talking about a little bit about the RAID and all that stuff. In a typical world, right, you will allocate it, 6 drives, right? Say if you do RAID 6, 4+2, 4 drives for data, 2 drives for this, right? It's always fixed, right? With our architecture, it is always varies, right? Depends on the size of the cluster, depend on the size of the file, how you would, if it's a small file, you stripe it across 3 nodes as an example. Yeah. Larger files, stripe it across a larger number of nodes. You add more nodes to the cluster. So there is a lot of variability already as part of the cluster built in, right? So depending on the size of the file, depending on how large your cluster is, depending on how you want to protect it.
You don't know your size of your file when you're ingesting.
Yes. So there are lots of say for example you start with a small cluster and you say, okay, my protection level that I want is that I can tolerate 2 drive failures or 1 node failure, right? Tomorrow you say, no, I'm putting a lot of data. I think 2 drive failure is low. I want to make it a 3 drive failure tolerance, right? I could dynamically just go, change that, and boom, that's it. I don't have to go and restripe my file system. I don't have to go and restripe anything. It just changed like that.
So to answer your question more directly, it's that we do the variability at a different level. We do it in the stripe size level and the way we vary that. And for large files, that makes the biggest difference. And for, keep in mind, I don't mean a 1 terabyte file when I say large files. I mean like anything over a meg.
Well, 128K is considered a small file, right?
Well,
yeah.
I mean, yeah, it depends on which architecture you're talking about, meaning a small file. I mean, even today, that's not that small.
Yeah.
But the answer to your question very specifically, if even I could change that 8K block to a smaller block, it would make very little difference to the storage efficiency of Isilon. Even if I could make it a 1K variable, just for the way we've done our architecture, it just doesn't. We just don't need it.
How do you manage deduplication and compression?
Yeah,
Great question.
So hold that question. So I'll come back to that in 1 second. So the nodes, just quickly, and because I'll try and come back for time. So there's a spread of nodes. So imagine this is performance and this is capacity, very generally, obviously, right? You've got very dense archive nodes down the bottom left, all the way up to the fastest all-flash nodes up on the top right. And you can pick any portion of these. So for example, you might have a tier of all flash and then a massive amount of archive. And it all depends on your workflow. At the Unstructured Data Solutions Group, so within Dell Storage, we're very focused on what the customer's use case is. That's the biggest thing to take away from this as far as how pre-sales work differently to the rest of the organization. So we're all about learning your workflow and learning how we can plug it in to all the features that we have in OneFS to make it, better and the integration better. Yeah, so I'll keep going unless there's any questions.
Oh, are there any limitations on the number of nodes that you can have?
So today it's 252 nodes. It's the largest cluster. You remember the difference with Dell, it's the EMC heritage, I suppose, is when we give a number, we give a validated engineering number. We don't just give a theoretical number. If we gave theoretical numbers, we'd have clusters that were just absolutely gigantic, but we'd never actually test it. So 252 is our current tested, validated thing, and we validated that with all of these features. All the next features will be on the next slide. Yep.
So this is sort of these numbers which you're seeing out here. So this is assuming that if I take an A200 node and I put 252 of those A200 nodes, that's basically your 44 petabytes of, in a single cluster, a single file system you're going to get.
Yeah, and it actually can be more than that, and I'll explain why in a second. So these are the various different features that we have. I won't go into each of these in too much detail, mainly that we obviously have a very common naming convention you can see here, the word smarts in a lot of them. So the ones we haven't talked about, which I don't have a slide on, is the SyncIQ, the snapshot, and the smart lock. So SyncIQ is our disaster recovery, replication. Snapshot is our policy-driven, everything's policy-driven, but policy-driven snapshotting system. So you can say, hey, I have this directory, I want to snapshot it every, 2 minutes or 5 minutes or whatever, and I want to keep that snapshot for 60 days and offer it to my users for self-service recovery, stuff like that. Smart lock is really quite an interesting one. Smart lock is write once, read many, so it allows you to do sort of archive workloads where you can lock the file system. So the Isilon will protect a customer's data. So think like a bank or an insurance company that wants to write a PDF where you signed your life away to some policy that you paid a lot of money for. They need to keep it there so they know that it's never altered, and that is actually Sec 17A compliant. So you can go through the full thing for financial organizations. And quotas is just a way to quota this file system to allow it to appear bigger and larger if you require. And each one of these you could spend a lot of time on how they all work, right?
Are all these options free? They come with their standard licensing?
So some of these options are free depending on how it is, but generally they're all licensable. Cloud Pools is the one exception to that. Smart Connect at a basic level is free. Cloud Pools is to all Dell technology products. Everything else there is a licensable product. And that's because a lot of customers don't. The reason people ask us, why do we do that? And the reality is a lot of customers don't use a lot of these features. They might only want replication and smart pools. So we give them the flexibility to do that. So the 3 approaches to data protection, this goes back to the question of, how do we deal with data reduction? So we have a couple of methods. Obviously, we've already spoken to data efficiency, which we're not talking about here. This is just data reduction. So reducing the logical data down. So we have inline compression and deduplication that we offer on our latest systems. For example, our F810 actually has a hardware offload card to do inline compression. And the reason we do that is so that we can maintain the data reduction capabilities while not impacting performance. So we've had a lot of successful proof of concepts up against competitors where we've been compared to like for like, and they can see why we made that choice. So that's how that works. Obviously, zero detect, compress, inline deduplication to do all the magic on the fly. We then have a separate process that we can do for post-process deduplication. So this might be for like a workload that's more archive-like and they're not worried about it long-term as it comes in. And so they want to do it just post-process. So it's a lot less...
Can we say also that the first method is better for Flash because you don't want to waste too much?
That's effectively,
Absolutely,
absolutely. That's right. So basically, the number one is basically our all-Flash platforms, as you say. Number two is any of our platforms can do number two.
That's right.
Yeah.
But the number two, is it scheduled like every weekend or every night?
Yes, it's a job. It's a job that runs on the cluster.
Can I decide when I run this?
Yes, you can decide when you run all the jobs, what impact levels they have, how they'll talk to the cluster, how much resources they use, all this sorts of stuff.
Okay, so also the priority.
Priority, all that sort of stuff. Yeah, there's a lot of IP in making a distributed cluster and file system work well. And part of our IP is exactly that, how you do jobs at scale. If you go to Treewalker file system that's got 60 billion files in it, the answer is you don't. So we have technologies underneath the hood that can do that. Do snapshots in a period of time, and we can understand the changes between the systems so we can keep that up to date. So we don't have to do these crazy things.
Do you have any system to monitor what is happening and give me indications like, the trends or analytics so they can decide and they can take decision on top?
From a capacity file analytics perspective, we have that. From a performance perspective, we have that. We also plug into things like Grafana. You can manage an Isilon with a script if you want to, and which means all the APIs that we pull for performance data, you can also get that for any other system. So some customers come to us and they want to plug their specific monitoring system into it. We can hand them the API guide and say, this is what we use. Here's some metrics we think for your cluster. Go ahead and do it yourself.
Yeah, and in the next part, we are going to talk a little bit about the insights that we're going to talk about, some of the new stuff. So let's hold up.
We'll get, And then obviously there's a small file packing, right? Where we can, again, it's policy-based, it's a job. You can tell it which parts of the file system, or you can do the whole file system. You can say what types of files to look like, all this stuff. Now, it's all predefined. Everything in Isilon has a default that generally 99% of customers never change. But it is still configurable if you want to do that.
What happens if I'm doing this process? So I have a bunch of small files. They are packed in a big thing. And then I modify one file just in the middle. Do we have to do all the repackaging?
No, so we just treat that one file. So basically, we mark the old file in the container as no longer required. Like it's basically like blank space. The file then becomes part of the file system normally, and the next job that runs will pick up that and repack it if it needs to, if it's compliant, like if the change hasn't changed it.
This creates some fragmentation. So over time, you need another job to...
So then there's a job called a defragger job that will go through and check these containers, and it will look for that. So we have white papers and all that on the collection speeds, how that works, so we can give advice to our customers on what they want to use it for. It does imply a very tiny performance overhead, and that's just because there's another metadata redirector in front of it to tell it which container to go to, not just the actual metadata. So I'll continue on so we can get through this, get onto Monarchia. So just quickly on the automated tiering. So here we've got a three-tier system. Think of it as, say, Flash, one of our hybrid nodes, and say our archive, right? So you can have policies to move the data in between them. So we've already talked about that. That works great. And that's what the Emmy Award was actually effectively for, how this whole thing works, right? The other thing we can do, though, is we can move any of these individual files off to the cloud. And that feature we call cloud pools. Now, when we do that, that does actually stub the file. So it creates a link on the Isilon. The Isilon keeps the metadata for it. In other words, the locations of the objects used on the cloud. And then you can compress and encrypt it if you want to as well, because some customers want to do that.
Is that to a single cloud bucket, or can you have several, depending on the data, have it go to different clouds?
Totally configurable. So a lot of customers have more than one, or a business unit. A lot of people will divide a cluster up into multiple business units, and different business units will have, hey, I'm this particular vendor or whatever, but I want to talk to that.
Yeah.
We also offer our own private object cloud there as well, which is totally supported, of course. So, yeah. Okay. Again, all policy-based. Everything's transmitted, and I should just say that everything is transparent to the clusters, to the client. So the client coming in through NFS or SMB, a Windows user on one of your laptops, they don't know any different. They don't see, there's no icon that's different. It's just a different level of performance because we've got to retrieve it back before we can give it to you. We do caching, we do all sorts of things to make that experience the best. The other thing I just want to say about the unbounded scaling is while we can go up to, say, 50 petabytes in a cluster or whatever the numbers were on the last slide, we can tier virtually unlimited amount to a cloud. So you could tier 10 petabytes to a cloud. We only need to store the stub, or what we call a smart link file. That's a fraction of the size. So in certain situations, we can actually grow our clusters much larger than what that slide shows on the front end side. Just totally depends on what the customer wants to do and what they need from us. So then data protection. So obviously we've talked about snapshots. If you want to get the fastest way to RPO and RTO, so is obviously snapshots. We can then do sync IQ locally over a WAN or wide range over a WAN. And we also support technologies like NDMP. We plug in with most backup applications, all the standard stuff you'd expect. So that all works great, and it's dependable. It does what it needs to, so that's awesome. And then there's just one last thing, I think, and then is just this slide. Then there's a couple of quick things on what we've just brought out. So just as a quick last summary of the difference between two architectures, right? So if you go back really, really far back in the day, one of our old leaders talked about the various different types of architectures that you can have when it comes to these types of file NAS platforms. Generally, there's something called scale up, where you take two controllers, you put them together, you put a really fast link in between them, and they own all the RAID controllers and everything behind them. They carve everything up, and they present file systems out the front and LANs and all the rest of it, right? The next iteration to that was federated scale-up. That's effectively what the write is, and that's what a lot of competitors are, right? So they take one of these controllers, they call it a node, and then they stitch it together with an abstraction layer or a redirection layer in front of it. The main thing is, though, is it doesn't change the fact that there's still all the various components you have to manage there. So you've still got to manage the file system, all the constraints under it, and so that creates the single point of management on ours versus multiple points of management over here. We obviously do the automatic load balancing, so moving files around or moving the users around as we need to. Here we have got to manually distribute it, right? So obviously there's a disadvantage there. From a file system perspective, if we lose one node, it's still available because the file system's completely stretched across all nodes. We can rebuild that node, we can remove it, we can do all sorts of things. In this case, the data is just on that one controller head. So if they lose that controller head, they have problems with visibility into the actual namespace. And then client connects any node, specific systems. So just quickly, and I'll go through these in like 30 seconds.
Just a quick question. What's the max size of a single file or directory? What's the biggest of a single file? What's the biggest?
So the biggest of a single file is literally just gone to 16 terabytes.
And how about a directory? How big?
Directory can be whatever. There's really no limit. I mean, it just comes down to how the customer wants to structure that. You could put 16 terabyte files and put a heap of them in one directory and grow it to some crazy amount. Yeah. So these are just the last few things we've gone here is node upgrades. We've made some changes to do parallel node upgrades. We can divide a cluster into slightly different availability zones, and we can upgrade them separately, so that's all good. File system support. And the only other one I wanted to say was this, and then I'll hand back to Kaushik, and that is that we've recently released a CSI plugin for Kubernetes. We used to have our own provisioner that was based on a couple of different tools, but we've gone with the standard. So, yeah. And with that,
Yeah. And next session, when Audrey will be here, he'll talk a little bit more about some of these, some of the Kubernetes integration that we are doing, right? So across the portfolio. So thank you, Callan. So this is basically just in a nutshell, basically what Isilon is. Just wanted to give you a flavor of the architecture. What's so unique about it, right? Like as I said, I mean, the thing which I think is very cool is the fact that this cluster lives on forever, right? That it's always forever, whether you're doing software upgrades, hardware upgrades. And the second part of it is basically the flexibility. Like as I talked about, you were asking about the block sizes. It's so variable. You can start with a protection level. You can change the protection level. You can add clusters, add nodes, right? You can mix and match different types of nodes. You can have some flash nodes. You can have archive nodes, right? And it just adjust. In fact, there was someone who had said, "This is almost like water, right? It just keeps flowing, and then it just adapts, right, to your workloads, your needs, and so on, right? So that's basically in a nutshell, which is Isilon, and then and it comes with all the features and functionality that you would expect from an enterprise file system.